Hello students, welcome back. So today we are going to do some problem solving on concentration cell and some general electrochemistry problem solving. Beside that, we are going to cover an important thermodynamic property of the electrochemical cells. Okay, so I hope you have gone through all the lectures. This is a very important chapter. You can expect one definite question coming in JEE Advanced from this topic. So your doubts should be catered properly. So if in case you having any doubt, so if you want to take your doubts, so just send to us so that we can get back to you in no time. So let's start the lecture for today. So let us start with the question first. So yesterday we were discussing a very important concept of concentration cell. We did some basic level solving on concentration cell. Today we are going to do some more solving on concentration cell, and then we are going to solve some more high level problems. Okay. So let us look at this question. This says that the EMF of a given cell, a cell has been given to us, is 0.18 volt at 30 degrees Celsius. Okay, the cell is given to us. It says that find EMF of the cell when 40 ml of 0.2 molar NaOH is added to the negative terminal of the battery. Okay, so let us first understand what kind of cell is given to us, then we'll understand what has to be done in the question. Okay. So in case you want to solve it, you can pause and you can start solving and you can replay once you have solved the question. Okay. So if you look at this question, so there is a hydrogen gas and there is a hydrogen ion. So basically in the anode we are having hydrogen ion cell, that is a gas ion cell. Okay. And in the cathodic half or on the RHS side we are having H2SO4, which is again a source of acid. Okay. So this would which is again a source of H plus ion, which would give H plus ion, and then there is a hydrogen gas. So again in the cathodic half also we are having hydrogen ion and the hydrogen gas as the electrode. So you can clearly make it out that this is a concentration cell. Okay, the cathodic and the anodic half are similar. Okay, only difference is the concentration. Okay, so now this says that find the EMF when 40 ml of 0.2 molar NaOH is added to the negative terminal of the battery. Now we know that in a galvanic cell at anode oxidation takes place, so the electrons are pumped out, so it goes on the rod and through the rod with the help of the conducting wire it reaches the cathode. So anode has electrons on it, so it is called as the negative terminal. So we know that in a galvanic cell anode is the negative terminal and cathode is the positive terminal. Okay, so we are adding 40 ml of 0.2 molar NaOH in the anodic chamber. Okay, so we want to find the pH. Okay, so we can see that this HA which has been given to you is a this HA which has been given to you is a weak acid. So its pK is not mentioned anywhere. Okay, so what we'll do, first we'll find out the pKa of this HA or the weak acid. Okay, so let us just apply the formula. So we know that E cell is equal to 0.059, approximately we can take this as 0.06 into pH of anode minus pH of cathode. This we have derived in the previous lecture and we have solved some basic problems on this formula as well. Okay, so you can derive as well. But if you remember the formula, that would be that would be much better because you can directly solve the question. Okay, so E cell is given to us as 0.18. Okay, 0.180. This is given as 0.06. So I will just take this over here. So this is pH of anode. Okay, minus pH of cathode. Now let us look at the cathode. In cathode we are having 0.05 molar H2SO4. So 1 mole of H2SO4 gives 2 H plus ions or 2 moles of H plus ion. So 0.05 molar would give 0.1 molar of H plus. Okay, so the concentration of H plus in the cathodic half is 0.1. So its pH would be 1. Okay, I hope this is clear to you. Okay, so if you just do this is 6 3s. So pH at anode is basically 3 plus 1, that is 4. Okay. Now because HA is a weak acid, okay, so we know that a weak acid dissociate as H plus and A negative. So at time t is equals to 0, if C is the concentration of this, after time t, say alpha is the degree of dissociation, C alpha would dissociate, so this will lead to formation of C minus C alpha. So 1 mole of HA is giving 1 mole of H plus ion and 1 mole of A negative. So C alpha and C alpha of A negative would be formed. So we know that Ka is equals to C alpha into C alpha upon C1 minus alpha. So we can write Ka as C alpha square upon 1 minus alpha, because HA is a weak acid, so we can neglect alpha. Okay, we will assume that alpha is very small, so 1 minus alpha is approximately 1, so Ka is equals to C alpha square. Okay, so we will say that alpha is equals to root of K into C. Now we know that H plus, the concentration of H plus is C alpha, so we will write H plus as C alpha. So H plus would be C into alpha. We have already we have found out the alpha as root of K upon C, so this would be K upon C. So H plus over here would be root of K into C. Okay, so when you just like apply the log on both the side and take negative, so we'll get the pH as half of pKa minus log of C. Okay, this also we have derived in the previous lecture, so just this is for your revision. So we know that the pH of anode, because anode is made up of a weak acid, so pH would be half of pKa minus log C. Concentration we can see it is 10 raised to minus 1, so this would be log of 0.1, so this is given as 4, so I can write pKa as, this would be 4 into 2, 8, okay, and this would be plus 1, so it goes over here and it becomes 7. So pKa of this acid is 7. Okay, so the first information that we needed to extract from this question was to find out the value of pKa. Okay, I hope this step is clear to you. So this can be another question. Okay, so this would be given to you, EMF is given to you, you will be asked to find the pKa of the weak acid. So this is the way you calculate the pKa of the weak acid, which comes out to be 7. Okay, hope this is clear to you. Okay, so I will just erase this. If you want to take a snapshot, you can take a snapshot of this. Okay, so when we are adding NaOH in the negative terminal, so negative terminal is the anode. Okay, so we are having acid in the anodic chamber, a weak acid. Okay, and we are adding a strong base, so there would be a neutralization reaction, and this would result in the formation of salt plus water. So NaOH would react with HA and form Na plus water. Okay, so we know that initial millimoles of HA. Okay, so molarity of HA is given to you. Okay, the molarity of HA is 0.1, volume is 100 ml. So we know that number of moles is also equal to molarity into volume, but if volume is in milliliter, so we'll get the number of millimoles. So 100 into 0.1 is the millimoles of HA. Okay, so millimoles of NaOH would be 40 into 0.2. Molarity is number of moles upon volume, so number of moles would be molarity into volume. Because volume is in ml, so we'll get the moles as millimoles. So 40 into 0.2, this would get as 8. Okay, now you can clearly see that they are not taken in the stoichiometric ratio. NaOH is taken less and HA is present in excess quantity. So NaOH will act as a limiting reagent. We know that 1 mole of NaOH is reacting with 1 mole of HA. So 8 moles of NaOH would react with 8 millimoles of NaOH would react with 8 millimoles of HA. Okay, so the final millimoles left would be 2 over here, 0. Okay, so this is completely consumed. So we'll say that NaOH is the limiting reagent. 1 mole of NaOH forms 1 mole of Na. So 8 millimoles would form 8 millimoles of Na. Okay, so in the final solution, when we have mixed 40 ml of 0.2 molar NaOH in the negative terminal, so in the final solution, in the final anodic chamber, we will have 2 millimoles of HA that is left and 8 millimoles of Na that is formed. Okay, so you can clearly see that in the anodic chamber now, we are having a weak acid HA. Okay, we are having a weak acid whose concentration would be number of moles upon total volume. So number of millimoles is of HA is 2 upon total volume is 100 upon 100 plus 40, that is 140, okay, because we have mixed two solution, so total volume would increase. Similarly, if you look at NaA, so the concentration of NaA in the anodic chamber would be 8, okay, moles upon total volume 140. Okay, now you can clearly understand that when you have added 40 ml of 0.2 molar NaOH, the anodic chamber will become a buffer solution, okay, because in the final solution we are having a weak acid HA and its conjugate which is A negative, or a weak acid and the salt of that weak acid with a strong base. So in the anodic chamber now we are having a buffer solution, okay. Hope this is clear to you. So we are having a acidic buffer solution when we have added NaOH in the anodic chamber. So the pH of anode, okay, would be found out by using the Henderson-Hasselbalch equation, which says that pH is equals to pKa plus log of concentration of conjugate upon concentration of acid. Okay, hope this is clear to you. So pH anode would be pKa we have already calculated as 7 plus log of conjugate. Now conjugate is NaA, so its concentration is 8 upon 140 divided by concentration of acid. Acid we know is concentration is 2 upon 140. So they will get cancelled out, okay. So we'll get pH of anode as 7 plus log of, okay, 7 plus log of 4. Okay, hope this is clear to you. So this will become log base 10 4 is 0.60. Okay, so pH anode would be 7.6. Okay, hope this is clear to you. Sorry. Just a little correction. Sorry, it's correct. Okay, so the pH at anode would be 7.6. Okay, so this is the basic equation that we are using. So we calculated the pH at anode, which is 7.6. Now because it is a concentration cell, so we can directly say that the E cell of this particular concentration cell would be 0.06 into pH anode minus pH cathode. Okay, so this is how you calculate the pH of anode. So finally we will say that E cell would be equal to 0.06 into pH of anode minus pH of cathode. Okay, hope this is clear now. So E cell would become 0.06, pH anode we have just calculated as 7.6 minus pH of cathode. Cathode we know it is made up of H2SO4. So 1 H2SO4 will provide 2 H plus ions, so 0.05 will provide 0.1 H plus. So the pH of the H2SO4 solution would be 1. Okay, so the answer of this would be E cell would be 0.06 into 6.6 volt. Okay, I hope this question is clear to you. So you can see that beautifully this ionic equilibrium chapter has penetrated into electrochemistry. Okay, so if you have the idea of the basic ionic equilibrium, good questions that are formed in this chapter will definitely touch a portion of ionic equilibrium. Okay, hope this is clear to you. Okay, so let's solve another question, something like this only. So we are having the same setup now. Okay, the concentration cell is same. Now in this case we have added, find the EMF when 50 ml of 0.2 molar NaOH is added to the negative terminal. Okay, so the question is same. Okay, so we'll use the data that we have got in the previous question. Okay, so we have calculated pKa of HA, that was 7. Okay, so we are going to use this data now. So this says that we are having HA and to the negative terminal we have added NaOH. Okay, so they will react together. This is a reaction between acid and base, so it would form Na plus Ha. Okay, so millimoles of Ha over here is molarity into volume. Okay, so this would be 10. Similarly, that of NaOH would be 15 to 0.2, which is again 10. Okay, now you can see that they are taken in the same stoichiometric ratio. Okay, so this would react completely, even this would react completely. 1 mole of NaOH reacts with 1 mole of Ha. So 10 moles of NaOH would react with 10 moles of Ha. So both of them will be consumed completely. Okay, so the millimoles of Na formed would be 10. Okay, so we need to find the concentration of Na. So this would be 10 upon 150, because the total volume of the solution became 150. Okay, because 200 ml you are adding 50 ml. Okay, so the concentration of the salt became 1 by 15. Okay, now you can clearly see that this is a salt of a strong base and a weak acid. Okay, Na is a salt of NaOH and Ha. So it is a salt of strong base and a weak acid. So the pH of the aqueous solution of this salt would be 7 plus half pKa plus log C. Okay, I hope this is clear to you. So now this becomes a case of salt hydrolysis. Okay, so the pH at anode would be 7 plus half. We know the value of pKa of the acid is 7. So this would be 7 plus log C. Now the concentration is 1 by 15, okay, of the A negative of the anion. Okay, so concentration would be of A negative. So this is 1 by 15. So log 1 by 15 is also minus log 5 minus log 15. Okay, so we'll just use that. So we'll say that this is minus log 15, or you can write this as plus log of 1 by 15. Okay, so pH anode would be, now log 15 is log 5 into 3, log 5 into 3, log 5 plus log 3. Okay, log 5 is approximately 0.69, okay, and log 3 is approximately 0.47. Okay, so we will calculate the pH at anode. This would be 0.69 plus 0.47 or 0.48. Okay, so pH at anode would be 7 plus half. Okay, this would be 69 plus 47. So this is 5.84. Okay, hope this is clear to you. So just you can calculate from here. So this would be 2.92. Okay, so this would become 9.92. Okay, so and we know that the pH at cathode, because cathode is made up of sulfuric acid, so pH of cathode would be 1. Okay, so we can directly use the formula E cell equals to 0.06 or 0.059 pH of anode minus pH of cathode. Okay, so you can calculate this. Okay, so this would be the answer. Okay, I hope this is clear to you. Just look at the steps that we are doing. First, we are adding, okay, NaOH in the negative terminal, that is we are adding it in the anode. So after adding this, all the Ha would be consumed. So we'll form a salt. Okay, now because of salt hydrolysis, this anodic chamber would become basic. So the pH of this would be 7 plus half. Okay, pKa plus log C. Similarly, if you put the value of pKa, which we calculated in the previous question, okay, the concentration we know it was 1 by 15, so I can write this as minus log of 15. Okay, so I will just put the value. Okay, if you directly remember the value, but in JEE question generally the log value would be given to you, so don't worry about that. So this is approximately 1.16. okay, log 15 is 1.16. okay, so you just subtract it from 7, so that would be 5.84. so divide by 2, so that would become 2.9. okay, 2. So the pH at anode would be 9.92 and pH at cathode is 1. So we'll use the direct formula that we had derived in the previous lecture. So we'll get the value of pH. Okay, so you can see that this is a beautifully crafted question. This covers the basic concepts of electrochemistry, concentration cell, as well as the ionic equilibrium. So this becomes a very important segment in this chapter. Okay, so now let us look at this question. Okay, this says that the EMF of a cell is given to us as minus 0.6 at 298 Kelvin. This says that AgNO3 is 80% dissociated and KBr is 60% dissociated. Calculate KSP of AgBr. Okay, so let us solve this question now. Okay, so let us look at the anodic chamber first. Okay, so in anodic chamber we know that there is a silver, okay, and silver nitrate is the electrolyte that is in the solution. So this is basically metal dipped in a metal ion solution, so that would undergo oxidation. Okay, now at the cathode, now if you see the cathode, there is a Br negative, AgBr and then Ag. So this is a metal insoluble salt, common ion electrode. Okay, so that would undergo reduction. Okay, and it would form AgBr plus electron forming Ag plus Br negative. Now if you look at this, no data of their standard reduction potential is given. Okay, so one thing that can work over here, we can consider it as a concentration cell also. So what we are doing over here, we are just dipping silver, which is having a coating of its insoluble salt in the bromide solution. Okay, so AgBr is a sparingly soluble salt, so it would be entering into the solution. There would be an equilibrium between AgBr and the dissociated ions. Okay, so we can consider it in a different manner also. Now let us understand what I am saying. Okay, so if you look at this, so we can consider this as a metal ion electrode. Okay, a metal that is dipped in the metal ion solution. Okay, now that metal ion, the concentration of that metal ion can be calculated, okay, by taking a sparingly soluble salt with a common ion in it. Okay, so we know that AgBr is splitting into Ag plus and Br negative. Okay, the solution already has the Br negative in it. Okay, because this is a metal rod. Okay, we have applied a paste of the insoluble salt and we have dipped into the bromide ion solution. Okay, so AgBr would dissociate into Ag plus and Br negative. Okay, all the Br negative would be coming from the aqueous solution only, because AgBr itself is a sparingly soluble salt. So the Br negative that would be coming from AgBr would be very small. Okay, so some amount of Br negative is coming from AgBr and there is a huge amount of Br negative in the solution. So the total Br negative solution would be taken, the total Br negative coming in the solution would be taken, that is directly coming from KBr. Okay, so we will neglect that of Br negative that is coming from AgBr. So from that data we will get the value of concentration of Br negative. Okay, now we know that solubility product is Ag plus into Br negative. So we know the value of Br negative, the concentration of Br negative. Okay, so we will find out the concentration of Ag plus. Okay, so what I am going to do is I am going to consider it as a metal dipped in a metal ion solution. Okay, now the concentration of metal ion is different from here. Okay, now this metal ion concentration would be, okay, as something like a sparingly soluble salt with a common ion in it. Okay, so if you write the overall cell reaction, so Ag would get cancelled out. So this is Ag plus from the cathode is changing into Ag plus aqueous, that is coming from anode. Okay, so E0 cell, because it is a concentration cell, so E0 cell would become 0. Okay, so if the oxidation potential is X, reduction potential would be minus X, so eventually the E0 cell would be 0. So if you apply the Nernst equation, so we will say that E cell equals to 0 minus 0.06 upon 1 log of concentration of Ag plus coming from anode, okay, divided by concentration of Ag plus coming from cathode. Okay, now Ag plus from anode is 0.1, but it is written that AgNO3 is only 80% dissociated. So when AgNO3 dissociates, into Ag plus and NO3 negative. Because it is only 80% dissociated, so the concentration of Ag plus would be 0.1 into 0.8. Okay, if it was 100% dissociated, then it would have been 0.1 into 1. The concentration of Ag plus would have been 0.1 into 1, but because it is 80% dissociated, so the concentration of Ag plus would be 0.1 into 0.8. Okay, so we know the value of E cell, that is given as minus 0.6 divided by 0.06 would be equal to log of Ag plus coming from anode divided by Ag plus coming from cathode. Okay, so you can clearly see this is 10. So if you take the anti-log, so this would become Ag plus at anode divided by Ag plus at cathode equals to 10 raised to minus 10. Okay, so I hope this is clear to you. Okay, so we'll say that Ag plus, okay, at the cathode, oh sorry, this is minus 0.6. Okay, so they will cancel out, so this will become 10 raised by 10. Okay, this is minus 0.6 and this is a minus over here. Okay, so this will become 10 raised by 10. Okay, so Ag plus at cathode would be Ag plus at anode into 10 raised to minus 10. Okay, so Ag plus at cathode will be, okay, 8 into 10 raised to minus 2 into 10 raised to minus 10. Okay, this is the concentration of Ag plus coming from anode. So Ag plus coming from cathode would be 8 into 10 raised to minus 12. Okay, I hope this is clear to you. Okay, now the Br negative in solution. Okay, the Br negative in the cathodic chamber, because now it is written that Kbr is 60% dissociated. So the Br negative concentration in the solution would be, okay, 60% of this. So this would be 0.6 molar. Okay, so this is the concentration of Ag plus in the cathodic half and the concentration of Br negative in the cathodic half. So the Ksp of this AgBr would be concentration of Ag plus into concentration of Br negative. So when you multiply them, so this will become 48 into 10 raised to minus 13 molar square. So this would be the solubility product of, okay, this would be the solubility product of AgBr. Okay, so look at the steps. First understand the steps, then I'm again going to demonstrate it what we have done. So whenever a metal insoluble salt and a common ion electrode is given to you, you can also change it into a metal ion electrode. Okay, so what we are doing over here, this is a metal insoluble salt common ion electrode. So we have converted into a metal ion electrode, because if this was considered as a metal insoluble salt common ion electrode, we should have written the reaction at cathode as AgBr taking up the electron and changing into Ag plus Br negative. So what I am doing is I am just converting it into a metal ion electrode. Okay, and the concentration of this metal ion, okay, the concentration of this metal ion is calculated by considering that AgBr is dissociating in the Kbr solution. Okay, so we are basically having a Kbr solution, and into this solution we are also having AgBr. So this is basically dissociation of AgBr in its common ion. So AgBr would dissociate as Ag plus and Br negative. Okay, and Kbr would break into, Kbr is a strong electrolyte, it would break into K plus and Br negative. So all the Br negative would be coming from Kbr only in the solution. Okay, so from that we will calculate the concentration, we can calculate the concentration of Ag plus if solubility product is given. Okay, so this is how you do this question. I think someone asked me this doubt yesterday. Now I hope this is clear to you. So whenever a metal ion electrode and a metal insoluble salt common electrolyte is given to you. So what you are going to do it over there is, you can convert the metal ion electrode into metal insoluble salt common ion electrode into metal ion electrode. Okay, now once we have converted into metal ion electrode, we need to find the concentration of metal ion. Okay, because we had taken insoluble salt, so we didn't know the concentration of the metal ion. So for the calculation of the concentration of metal ion, we will use the concept of ionic equilibrium, that is the insoluble salt AgBr is having a common ion in the solution, that is Br negative. Okay, so that you can also write it as, you can take a snapshot, I will just explain it. Okay, so you can also calculate this as AgBr was breaking into Ag plus and Br negative. Okay, so let the solubility of this salt be S, so this would be S and this would be S, and there is a common ion, okay, that is Br negative. This would be 100% dissociated. If nothing is written, then it is 100% dissociated, but it is written over here that is 60% dissociated. So we will find the concentration of this. So the total concentration of Br negative would increase. Okay, so due to this reaction would go to the backward direction. So we will say that the value of S would be very less. So this would be approximately equal to C. So we will say that Ksp is equals to concentration of Ag plus into concentration of Br negative. So we know the concentration of Br negative. Now we can calculate the concentration of Ag plus. Okay, so once you have calculated this Ag plus, now this can be treated as a metal dipped in its aqueous solution containing the Ag plus ion. Okay, let me take an example so that you understand it. Suppose we are having a cell something like this. So we are having silver chloride, and say we are having KCl, okay, whose concentration suppose is given to us as 0.1 molar. Okay, there is a salt bridge, then we have been given KBr, say it is again 0.01 molar. Okay, now there is a AgBr and Ag. Okay, so now suppose the value of Ksp of AgCl is given to you as say 10 raised to minus 10, and Ksp of AgBr is given to you as 10 raised to minus 12. Okay, you need to find the EMF of this cell. Now you can see that E0 is not given to you. Okay, E0 of the reduction or the E0 of the cathodic or the anodic half is not given to you. So what I will do, I will convert this, okay, cell into a metal ion electrode. So I will say that this can be taken as a metal ion electrode. Okay, what we need to do, we need to calculate the concentration of this Ag plus ion. Now we know that we have taken a KCl solution, and in that we have dipped a silver rod containing the paste of AgCl. So AgCl would be dissociating into, okay, AgCl would be dissociating into Ag plus and Cl negative. Okay, so let the solubility of this be S, so this would be S, this would come out to be S. Cl negative we know is 0.1 molar, so the concentration of Cl negative would be S plus 0.1, so we can take it as 0.1. Because of the common ion effect, this reaction will go in the backward direction, so the value of the solubility will decrease. Okay, so S plus 1.1 would be approximately equal to 0.1. So we can say that S, which is the concentration of Ag plus in the solution, into 0.1 equals to 10 raised to minus 10. So Ag plus we will get it as 10 raised to minus 9. Okay, so the concentration of Ag plus in the anodic half is 10 raised to minus 9. Now let us look at the cathodic half. So in the cathodic half, I am again saying that we will convert this into metal ion electrode. Okay, now we need to find the concentration of Ag plus. So AgBr would be dissociating into Ag plus and Br negative. Okay, so let solubility of this be C. Okay, so this would break, this would result in the formation of C concentration of Ag plus and C concentration of Br negative. Now Br negative is also coming from Kbr, so the total concentration of Br negative would be C plus 10 raised to minus 2. Okay, so the Ksp would be C into C plus 10 raised to minus 2. Now because of common ion effect, this reaction would go in the backward direction, due to which the value of C would decrease. Okay, so we will neglect the C. So C is also the concentration of Ag plus, so this would be Ksp, which is 10 raised to minus 12 upon 10 raised to minus 2, which is 10 raised to minus 10. Okay, so this would turn out to be the concentration of Ag plus at anode would turn out to be 10 raised to minus 9, and concentration of Ag plus at cathode would turn out to be 10 raised to minus 10. Okay, now we know that at anode oxidation would be taking place, Ag would be changing into Ag plus electron. At cathode, Ag plus would be undergoing reduction, Ag plus would be taking electron and changing into Ag. Now this is as a concentration cell, E naught cell would be 0. So EMF of this cell would be 0 minus 0.06 upon, okay, N is 1 divide into log of Ag plus of anode divided by Ag plus of cathode. So we know the value of Ag plus of anode and Ag plus of cathode. Okay, so this is how you can deal with such kind of question. Okay, you can always convert it into a metal ion electrode. The metal insoluble salt common ion electrode can be converted into a metal ion electrode, and you can solve it accordingly. Okay, for that you need to find out the value of the metal ion concentration. So the metal ion concentration can be calculated just by using the solubility period concept, okay, and the concept of the concept of common ion effect rather. Okay, hope this is clear to you. Okay, so this is again a very good application question. So a lot of questions are formed on this as well. Okay, so let us look at this question now. So this says that we are having a cell, okay, we are having at anode we have taken silver, and the silver rod is dipped in the aqueous solution containing silver chromate. Okay, the solution is saturated, and at the cathode you can see that silver ion, okay, is having a concentration of 0.1 molar and a silver rod is dipped in it. Okay, so just write the equation. So we know that at anode the silver would be getting oxidized as Ag plus electron. Okay, at cathode the silver ion would be getting reduced. Okay, so this would take up the electron and change into silver. So overall reaction that would be happening, we can cancel the electron. So this would be Ag plus aqueous coming from cathode, okay, is changing into Ag plus aqueous that is coming from anode. Okay, because it is a concentration cell, so again E naught cell would be 0 because the oxidation potential would be negative of the reduction potential. Okay, so we can use the formula of E cell equals to 0 minus 0.06 upon N is 1 over here into log of concentration of Ag plus at anode divided by Ag plus at cathode. Okay, so the EMF is given to you as 0.18. So this is 0.18 equals to minus 0.06 into log of silver plus that is present at anode divided by silver plus that is present at cathode. Okay, so you can clearly see this is minus 3. Okay, just take anti-log, so this would become 10 raised to minus 3. So this would be Ag plus at anode into Ag plus of cathode. Okay, hope this is clear to you. So we are just using this. Okay, E cell was given to us as 0.8. This is minus 0.06. So you can just cancel out. So this will become 10 raised to minus 3. This would be equal to Ag plus at anode divided by Ag plus at cathode. Okay, so we need to find the Ag plus at anode. Okay, because we don't know the concentration of this Ag plus. So Ag plus at anode would be Ag plus at cathode. Cathode we know the concentration of Ag plus is 0.1. Okay, so the concentration of Ag plus at anode is 10 raised to minus 4 molar. Okay, now where, okay, I hope this is clear to you. Now from where this Ag plus is coming, now it is written in the question that Ag plus is coming from a saturated solution of Ag2CrO4. Okay, so when you are dissolving Ag2Cr2 in aqueous solution, so you would be getting 2Ag plus aqueous plus chromate ion aqueous. Okay, so let the solubility of this be S. Okay, so we know that this 1 mole of silver chromate is forming 2 moles of silver ion. So the S portion which is soluble would form 2 S moles of Ag plus and S moles of chromate. Okay, now we have just calculated the concentration of Ag plus in the anode, which was 10 raised to minus 4. So we will say that 2S is equals to 10 raised to minus 4. So S would be 10 raised to minus 4 by 2. Okay, so KSP in this case would be Ag plus concentration whole square into chromate ion concentration. Okay, so if you put this, this becomes 4s cube. S, you know, it is 10 raised to minus 4 divided by 2. So you just plug that value in this. If you plug that value, S 10 raised to minus 12 divided by 2 cube would be 8. Okay, so this would get half. So this would become 5 into 10 raised to minus 13 molar cube. Okay, so this would be the answer. I hope this is clear to you. So this is a very standard question that can come in your JEE. Okay, so just have a look at the steps. So this is saying that we are having a silver that is dipped in a solution which is saturated with Ag2CrO4. That means Ag2CrO4 is saturated. That means whatever amount of Ag2CrO4 can dissolve in water has been dissolved over there. So a equilibrium would be established. Okay, so we'll get 2 Ag plus and chromate ion. Okay, so let S be the solubility of Ag2CrO4. So 2S amount of Ag plus would be in the solution and S amount of chromate ion would be in the solution. So Ksp of this sparingly soluble salt would be concentration of Ag plus whole square into concentration of chromate ion, that would be 4S cube. Okay, and now you just have to calculate the value of S. Okay, so we'll just write the anodic half, cathodic half, overall cell. We are going to write the Nernst equation. So E cell would be minus 0.06 into log of concentration of Ag plus at anode divided by Ag plus at cathode. So from this you will be able to get the value of Ag plus at anode, okay, which we calculated at 10 raised to minus 4. So basically 2S is equals to 10 raised to minus 4. So S is 10 raised to minus 4 divided by 2. So just put the value of S as 10 raised to minus 4 by 2, you will get the answer. Okay, hope this is clear to you. So these are the fundamental, or you can say these are the little tricky and difficult questions, but if you see the logic, if you see the way we are solving, it is not that difficult. It requires a basic conceptual approach of ionic equilibrium as well as electrochemistry. Okay, so let us look at this question as well. So there two reactions has been given to us in which NO3 negative is changing into NO2 in acidic medium and NO3 negative is changing into NH2OH in acidic medium. The reduction potential of both the half cell is given to us as 0.8 and 0.74. Okay, the question says that at what pH both half cells will have equal tendency to get reduced. Okay, so take RT by F as 0.06. Assume the concentration of all the species to be unity. Okay, so if you look at this question, so let us just see NO3 negative is changing into NO2. So we'll just complete this reaction. We know that one oxygen from here to here, one oxygen is getting reduced. So we'll add 2H plus over here. Those 2H will take an oxygen and form a water over here. Okay, so total charge here is +1. So we'll add an electron. Okay, so if we look at the second reaction, so in that NO3 negative, okay, is changing into NH2OH. Okay, now you can clearly understand that when you are going from reactant to product, there is a loss of 2 oxygen. Okay, so to take out 2 oxygen, we would need 4H plus. Okay, so 4H plus would take up 2 oxygen and form 2 water. Now also we have to add 3 hydrogen over there. Okay, so 4H plus will take up the 2 oxygen and we have to add 7H plus so that the remaining 3 hydrogen gets attached and it forms NH2OH. Okay, so this would be plus 2H2O. Okay, so this is a balanced reaction. Okay, hope this is clear to you. Now the total charge in the reactant, this is +7 -1, that is +6. Okay, so we will add 6 electron over here. So these are the balanced equation in acidic medium. Okay, so this says that at what pH both have equal tendency to get reduced. Both will have equal tendency to get reduced when their EMFs are equal. Okay, so we are going to apply the Nernst equation and find the EMF. So E of this half would be, okay, we would find it to be E naught, which is given to us as 0.8, okay, reduction potential is given to us minus 0.06 upon N was 1 into, now it is written that assume all the concentration of all the species to be unity. So NO2 is a gas, its concentration is unity, its atmospheric pressure, its pressure is 1 atm, the concentration of NO3 negative is 1 molar, okay. So this would be log of 1 upon H plus whole square, because you have to find the pH, so you cannot assume the concentration of H plus as 1 molar, okay. So E of this would become 0.74 minus 0.06 divided by the N over here is 6 into log of, okay, NH2H take it as 1 molar, NO3 negative as 1 molar, 1 upon H plus raised to power 7. Okay, so I hope this is clear to you. So we can write this as E will be equal to 0.8 minus 0.06 into log of H plus raised to a minus 2. So we'll take this outside. So this would become minus plus 0.12. Log of pH, I can write it as minus pH. Okay, so I can say that E would be 0.8 minus 0.12 pH. Okay. Similarly, if you look for this reaction, so you will say that E is equals to 0.74 minus 0.01 log of H plus raised to power minus 7. So you can take this minus 7 out, so E would become 0.74 plus 0.07. Okay, log of H plus is minus pH. Okay, so eventually this would become, okay, eventually this would become minus pH. Okay, so for them to have the equal tendency to get reduced, their EMF should be equal. So these two should be equal. So we can write this as 0.74 minus 0.07 pH equals to 0.8 minus 0.12 pH. Okay, so just bring it over here. So we'll get this as 0.12 pH minus 0.07. Okay, so that would be, and this would go over here. So this would become 0.8 minus 0.74. So this would be 0.06. Okay, I hope this is clear to you, and this would become 0.05. Okay, so pH would be 6 by 5. Okay, so pH would be 1.2 in this case. Okay, so you can see that these questions are not difficult. Only the questions appears to be difficult, but if you have understood the basic concept and if you are able to understand what question is saying, then question becomes very easy. So you have to depend upon your reading ability and extracting out the important data from it. Okay, to have a very strong understanding about the question, I would always suggest you to solve more and more subjective problems, because subjective problem will fix a concept level inside your head. Okay, objective question doesn't give that edge. Objective question you can solve after completing a good amount of subjective questions in a chapter. Okay, so I hope this is clear to you, and I hope you have understood this. Okay, so let us discuss the variation of EMF of cell with temperature. Okay, now this we know from the equation of thermodynamics, that is change in delta G with respect to temperature at constant pressure is always minus delta S. Okay, so this is basically directly you can get from delta G is equals to delta H minus T delta S. Okay, so at constant pressure, okay, and constant, we'll say that change in delta G upon delta T is minus delta S. Okay, now we know that delta G is minus N into F into E cell. Okay, so just put the value of delta G as minus N into F into E cell. So if you differentiate it, or if you take a partial derivative, so NF is a constant, so it will come outside. So this will become minus N into F d of E upon dt. Okay, so dE cell upon dt is known as temperature coefficient of EMF, or EMF temperature coefficient you can say. Okay, so this is how you calculate the value of delta S. Okay, so this is just the application of the thermodynamics equation. Okay, so this you should know, that is d of delta G upon dt at constant pressure is minus delta S. Now we know that delta G is minus N into F into E cell, so just plug that value over here. Okay, so we will get delta S as minus N into F into dE upon dt at constant pressure. So this dE upon dt at constant pressure is known as temperature coefficient of EMF. Okay, now this is not there in main syllabus, it is only there in the advanced portion. That also, like, I have never seen questions coming on this, so you can say that this is not also there in advanced portion, but it can be asked in Olympiads. Okay, so let us look for the, now we have calculated delta S. Okay, so we will calculate delta H. Okay, so we know that delta G is delta H minus T delta S. Okay, so delta H would be delta G plus T delta S, as you can see it over here. Now delta G we know it is minus N into F into E cell, and delta S now we have just calculated it as minus N into F into dE upon dt. Okay, so we will just use those values. So delta H would become minus N into F into E cell minus N into F into T into dE cell upon dt at constant pressure. Okay, now you don't have to confuse this N with moles. Okay, this is basically the number of electrons transferred between cathode and anode during a reaction or during a overall cell formation. Okay, hope this is clear to you. You can take a snapshot of this as well. Now let us look at a question to understand the formula. Okay, so this is a question. This says that the temperature coefficient of a cell whose operation is based on the following reaction is 1.5 into 10 raised to minus 4 volt per Kelvin at 298 Kelvin. We need to find the change in the entropy for the following cell. Okay, so we will say that delta S is equal to minus, okay, just I have written it, N into F into dE cell upon dt at constant pressure. Okay, the value is given as 1.5 into 10 raised to minus 4. Okay, now you can clearly see that in this reaction, obviously Hg was in 2 plus state, it has changed into Hg. Okay, Pb was in 0 state, it has changed into Pb2 plus. So obviously 2 electron was exchanged between them. So the value of N would be 2. 1 Faraday we know is 96500 Coulomb. Okay, d by dt is 1.5 into 10 raised to minus 4. Okay, so this would be the value of delta S. Okay, so a direct question, you don't have to use anything, just you need to know the formula. If you forget the formula, don't worry, just remember one basic thing, that d delta G upon dt is always minus delta S. Okay, now you can derive it from here. You can just write, instead of delta G, minus N into F into E cell. Okay, so once you have written that, okay, so I hope this is clear to you. Now this is, sorry, this is plus. Okay, because this is minus, this will get cancelled out. So this is a plus over here. Okay, so the value will come out to be a plus. Okay, because delta G, d delta G upon dt is minus delta S. Okay, now you can say that delta G is minus N into F into E cell. So just plug this value over here. So we'll get it as N into F into dE cell upon dt at constant pressure. Okay, hope this is clear to you. Delta G is delta H minus T delta S. Delta H would be delta G plus T delta S. Now you can just put the value of delta S as N into F into dE cell by dt. Okay, so we'll get the value of delta H. Okay, so if you just know this basic formula, you can like do all the calculations. Okay, so you do have to remember this thermodynamics equation to solve. Okay, so let us look at another question now. Okay, so this says that we have to find Kc for this complex. Okay, so AgNH3 2+ is changing into Ag plus 2 ammonia. So basically this complex is dissociating, okay, into Ag plus and 2 ammonia. some thermodynamic values have been given to us. We need to find the value of Kc. Okay. So how do we proceed in such questions? Okay, this is again a very common question that you will find in most of the textbooks or most of the content. Okay. So two E naught value have been given to us. Okay. The one which is given to us is Ag plus Ag forming Ag plus forming Ag. Okay. The reduction potential is 0.8 and AgNH3 twice Ag ammonia, this is 0.37. Okay. So out of these two, if we want to form a overall cell using these two data, okay, so we know that the cathode would be the one which is having more reduction potential. So this has to act as a cathode and this has to act as a anode. Okay. So if this acts as a cathode, so we know that Ag plus aqueous would take up one electron and change into Ag. Okay. The reduction potential of this is given as 0.8 volt. Now this will act as an anode because its reduction potential is this. So if you look at this, this can be treated as a metal, okay, dipped in the solution containing AgNH3 twice plus and ammonia is also present in the solution. Okay. So we can write this as AgNH3 okay, plus this is getting oxidized. Okay. So I can write this as, because reduction equation has been given to you. So I can write this as Ag taking up 2 ammonia and changing into Ag NH3 twice plus electron. Okay. The oxidation potential of this would become, or if you want to write the reduction potential, you can write. So oxidation potential is minus 0.37 volt. If you add the two reactions, okay, so the Ag would get cancelled out. So it will be left with Ag plus aqueous plus 2 ammonia forming AgNH3 twice plus. Okay. The overall E naught cell would become reduction potential of cathode minus reduction potential of anode, or you can write it as reduction potential of cathode plus oxidation potential of anode. So that would come out to be 0.43 volt. Okay. Now you can see that we are getting the reverse of this equation. Okay. So this is the logic I am going to use. The two E naught value were given to us. I am going to combine them and form a overall cell. Okay. Now if you look at this, how I wrote this reaction directly. Now this is something correlating to metal insoluble salt common ion. Okay. So this is basically a metal complex, okay, and metal and ammonia. Okay. So basically this metal is combining with ammonia and forming this complex and electrons are getting released. Okay. So because you have to find the Kc, so if this reaction attains equilibrium, so I can just now reverse this one. Okay, I can just reverse this. Okay, I can write this as this. Okay, so the E naught of this would become minus, okay, this would become minus 0.43 volt. Okay, so I just reversed this equation. Now because you have to find the Kc, so we'll assume that after some time a equilibrium has been established. So I've just reversed this. So E naught would become minus 0.43 volt and they should establish a equilibrium. So when it establishes a equilibrium, we know that E cell is equals to 0. Okay, so I will write E cell equals to E naught cell minus 0.06 upon n. N is, clearly you can see that it is 1 log of Ag plus into ammonia whole square divided by concentration of Ag NH3 twice plus. Okay, so this is 0. So this would become E naught cell would be equal to 0.06 into log. Now you can understand that this is the value of Kc. Kc would be Ag plus into ammonia whole square divided by Ag NH3 twice plus. So this is Kc. Okay, so we know the value of E naught cell as minus 0.43, this is equal to 0.06 into log of Kc. So Kc would become 10 raised to the minus 43 by 6. Okay, I hope this is clear to you now. So this is pure logic, pure observation based questions, nothing difficult. Okay, if you have gone from the basic, if you have start from the basic, if you have dealt with all the different types of electrode properly, and if you have understood how you are writing the representation of it, and you know the basic of chemical and ionic equilibrium, then this is a very easy task. Okay, it is not difficult at all. You need to just check that whatever you are writing is correct and you are not like doing any writing mistake or writing some another data. Okay, that is the common mistake that happens with everyone. I can purely understand that. So you have the leverage to do it, but try to improve it. Don't try to just repeat it every time. Try to avoid those kinds of mistakes so that it becomes very strongly, okay, that your preparation becomes very strong. Okay, so I hope this is clear to you. Okay, so just have a look at the way I have solved it. So we have been given a metal ion electrode, and we have been given a metal ammonia and a complex electrode. Okay, so we have just combined them, and using these two electrode potential data, we formed the overall cell. Okay, because this was having more positive reduction potential, so I took it as a cathode, and this was having a less reduction potential, so I took it as an anode. Then I wrote the reaction for the complete cell. We got the E naught cell. Now we can see that we have to find the Kc of this reverse reaction. So I took the reverse of this, so E naught would become minus 0.43. Okay, so when it was establishing equilibrium, E cell would become 0. Okay, so I just wrote the Nernst equation. E cell is equals to E naught cell minus 0.06 into log of this quantity would become Kc. Okay, so we'll get the value of Kc over here. Okay, so I hope this is clear to you. Again, a very important question. Okay. Okay, so let us look at this question now. This says that the EMF of the following cell is 1.05 volt at 25 degrees Celsius. Okay, there is a platinum, hydrogen gas, 1 atmosphere. Okay, NaOH, NaCl 0.1 molar, AgCl, Ag solid. Write the cell reaction and calculate pKw of water. Okay, so now when like I was solving this, there is a very common confusion that comes to us. Okay, now you can see that there is no salt bridge over here. Okay, so this is a common confusion that arises in everyone's minds. Okay, so if you don't see a salt bridge, it doesn't mean that it is only one terminal. Okay, it means that we didn't use a salt bridge over here. We used a membrane. Okay, so we had a anode. Okay, and we had a cathode, but instead of a semi-permeable membrane, which was instead of a salt bridge which was used to neutralize the excess positive and negative charge and complete the circuit, we used a membrane, a semi-permeable type of membrane. Okay, now when oxidation was happening, so this would accumulate excess positive charge, and when reduction was happening in cathode, this would accumulate excess negative charge. Some ions from anode would diffuse into cathode, and some ion from cathode would diffuse into anode, but only that ion would interfere in that ion would diffuse into the other solution, that would not react with any of the ion present in the solution. Okay, so this is how you are representing such kind of equations. Okay, so in these cases we don't have a salt bridge. Okay, so basically we are having a semi-permeable membrane. So in the anode we were having oxidation, in the cathode we were having reduction. So in the anode there was an accumulation of excess positive charge, in the cathode there was accumulation of excess negative charge. To neutralize these charges, some ions crossed from cathode to anode or diffused from cathode to anode, and some diffused from anode to cathode, so that they maintain electrical neutrality and the flow of current would be constituted. Okay, so this is also known as EMF or cells with transference. Okay, because some ions are getting transfer, and with salt bridge it is also called as like we call it as a galvanic cell or electrochemical cell without transference. Okay, So from there a concept of transport number also came. We'll deal with all these kind of things, okay, once we have completed the chapter. So we are going to do such kind of electrochemical cells as well, okay. So I hope this is clear to you. Now you can understand that at anode we were having hydrogen, okay, and we are having a OH negative solution. So OH negative solution is basically will tell us the amount of H plus present in the solution. So this is basically hydrogen in the hydrogen ion electrode, okay. So and in the anode you can see that we are having chloride, AgCl and Ag. So this is basically metal insoluble salt common ion, and they are separated by a membrane and not a salt bridge, okay. So that's why I was saying that it is very important to have a very strong hold at different kind of electrodes. If you are comfortable with all kinds of electrode, then these types of questions are very easy to handle, okay. So let us write the reaction. At anode we'll say that oxidation is happening. Now we'll say that hydrogen and H plus ion is present, okay. So we'll say that H2 gas is getting oxidized into H plus 2 electrons, okay. We know that the oxidation potential of this cell would be 0, okay. In the cathode terminal, this is a metal insoluble salt common ion electrode. So we'll say that a reduction is happening. So AgCl would be taking up the electron and changing into Ag plus Cl negative, okay. So the reduction potential of this is given to us as 0.23, okay. So the first question was we needed to write the cell reaction, okay. So we'll just add this. You have to multiply this with 2. Now when you multiply, we know that the value of E naught won't change. So this would become H2 gas plus 2 AgCl solid changing into 2H plus aqueous, okay, plus 2 silver plus 2 chloride ion, okay. So this would become the overall reaction that is happening in this cell, okay. So E naught cell I can write as reduction potential of cathode, okay, which is 0.23 minus reduction potential of anode, or I can write it as plus oxidation potential of anode. So the E naught cell of this would be 0.23 volt. Okay. So I hope this is clear to you. Like see this, like questions on electrochemistry just starts from the inference of the representation. If you have inferred, if you had concluded the representation well, then the chances of solving the question becomes very high. Okay, so you need to understand the very basic concepts, the basic types of half cells. Once you have done with it, once you are comfortable with it, then you can easily solve any kind of question. Just a basic concept of equilibrium is required and the questions become very easy. Okay. So this is how we write the E naught cell. Okay. Now the EMS has been given to us as 1.05. We have calculated the E naught also. Now this says that calculate the pKw of water. Okay. So we'll just write the Nernst equation. So I will say that E cell equals to E naught cell minus, I am going to take it as minus 0.06. Okay. So you can take it as 0.059 also. So you can see that between cathode and anode 2 electrons are transferred. So the value of N is 2 into log of concentration of H plus raised to power 2 into concentration of Cl negative raised to power 2. Okay. In the product it is H plus and Cl negative. AgCl is a solid. Okay, divided by the partial pressure of hydrogen. The partial pressure of hydrogen is given as 1 atm. Okay, so this is the expression of the overall EMF of the cell. Okay, so I can write this as 1.05 equals to 0.23 minus 0.03 into log of H plus whole square into Cl negative whole square. Okay, so you can take this 2 outside, so this would become, and you can also take 0.23 over here, so this would become 0.82 equals to minus 0.06 into log of concentration of H plus into concentration of Cl negative. Okay, so you can get the value of H plus into concentration of Cl negative as 10 raised to the minus 82 upon 6. Okay, I hope you can calculate this. So you have to use calculator, obviously you cannot do it. So the concentration of Cl negative is given to us as 0.1 molar. So from there you will calculate the value of H plus as 10 raised to the minus 82 by 6 divided by 0.1. Okay, so this way you will be able to calculate the concentration of H plus ion. Okay, so this would be the concentration of H plus ion. Now this H plus ion is coming from the anode, so the concentration of H plus ion is this. The concentration of OH negative is 10 raised to minus 1 or 0.1 molar. Okay, so you need to calculate the Kw of water. Okay, so Kw of water we know is concentration of H3O plus into concentration of OH negative. Okay, so just 0.1 into 10 raised to the minus 82 by 6 divided by 0.1. Okay, so this is Kw. So Kw would be 10 raised to the minus 82 by 6. Okay, we need to find the value of pKw. Okay, we need to find the value of pKw. So pKw would be minus log of Kw. Okay, now Kw you can see it is 10 raised to the minus 82 by 6. So when you calculate this, this would become 82 by 6. Okay, so 82 by 6 would be 13, 6 is 78. So this is close to 13.7. Okay, so this would be the value of pKw. Okay, so you can see that these questions are easily, you can calculate it. Okay, you don't have to use the calculator also. Okay, so if it was asked find the concentration of H plus, then some value would have been given to you in the question. Otherwise you can see that I am solving it without calculator. All the questions which we have done today I have solved it without calculator. Okay, so I hope you understood how to solve this problem. Okay, these are again very classical examples. I can say these are difficult level questions that can be asked in your paper or in your JEE examinations. Okay, so I hope you have understood today's lecture. Okay, so this is it about the galvanic cell and the electrochemical cells. Okay, from the next lecture we will start with another portion of this chapter, that is electrolysis. So for 2 lectures we will be dealing with electrolysis. After that we will enter into the another portion of this chapter, that is conductance and conductivity. So overall this chapter is little big as compared to the other chapters which we have done. So the credit of this chapter is also very high, just like thermodynamics as well as the equilibrium chapter. Okay, so the 3 chapters are there in the core which you should know, that would help you to score a lot of good marks in your paper. Okay, you will definitely get a question on electrochemistry in your JEE advanced paper. Okay, so in the next lecture we are going to start the electrolysis portion of this. Simultaneously we will be solving 1 or 2 small questions of electrochemical cells every day, so that the concepts are not forgotten. Okay, and beside that we are going to cover the electrochemical electrolytic cell and the conductivity cell portion. Okay,